Now, the last section of Chapter 3 is about matrix transformations. Now, what we're going to see in this section is that by writing vectors as column matrices, we can realize the job performed by a vector function, which we'll call a transformation, as left multiplication by a matrix of the appropriate size. Now, not every vector function can be expressed like this, but straightforward ones that perform transformations such as flipping the direction of a vector, stretching or compressing it, or even rotating it about an axis are examples of ones that can be. And the reason is that all of these transformations have a property in common, and we say that they are all linear. Now let's get down to the details and formulate exactly what that means. So we'll start from the beginning. Now a vector function, and you notice I just wrote the word function, because vector functions are still functions. We don't need to explicitly say that they're vector functions, because that's clear from this notation here. That's clear from writing down the function header. So really this is a vector function t in this definition, but we don't need to call it a vector function. There's nothing wrong with just referring to it as a function. So remember what this notation means. This means we have a function called t, and it takes as input a vector in Rn, so a vector with n coordinates, and gives you back as output a vector with m coordinates. So it's understood in the background, which I will actually take a moment to clarify that m and n are just two positive counting numbers. So they're the number of coordinates in the input vectors and the output vectors of this function t. Okay, so let's get to the definition now. A function t that is of this form, that goes from Rn to Rm, is called a linear transformation. If the following two conditions hold. So here are the two conditions. These are mathematical statements that have to be interpreted carefully. So the first one says that t of x plus y, and I'll actually quantify what x and y are in just a moment, but for now they're vectors that come from somewhere, but I'll have to finish. By the time we finish the sentence, we'll know exactly what we mean by x and y. So, but the statement is that t of x plus y, so before I go any further actually, let's pay attention to what this is saying. We've got two vectors x and y, and this plus sign says to add those two vectors. Now the result of adding two vectors gives you back, as a result, another vector, which is being plugged into the function t. So that's what this notation means. But the statement is saying that that is actually equal to t of x plus t of y. And this has to be true for every possible choice of vectors x and y in Rn, which is the domain of this function t, right? This is the domain, what you see here. The first thing before the arrow, this is the domain of the function t. Okay, so really what this is saying is that if you have two vectors x and y that are both n-dimensional vectors, you can either add them up and then plug them into the function t, or on the right-hand side of the equation, you can see that each of the vectors x and y are plugged into the function t separately and then added afterwards. So this addition here, this is actually addition in m-dimensional space, right? This addition takes place in Rm because this is a vector in Rm because it's an output from t. And this function header here tells you that the output from the function t is guaranteed to be an m-dimensional vector. So t of x, this is an m-dimensional vector, and t of y, that's also an m-dimensional vector. So we're adding two vectors in Rm here with this addition sign. But this addition sign, we're actually adding two vectors in Rn, right? Because x and y are in Rn for the purposes of this statement. So that's the first condition that has to hold. If you have two vectors in Rn, you can either add them and then plug them into t, or you can plug them into t separately and then add them afterwards. That's what this equation is saying. You're going to get the same result either way. Now the second condition says that t of k times x, and I haven't mentioned what k is, or even as far as this statement goes, I haven't even mentioned what x is yet. But again, just like with the previous statement, we're going to quantify it by the end of the sentence. But this condition says that t of k times x is equal to k times t of x for every vector x in Rn and scalar k. Okay, so that's That's saying what? That's saying if you have a vector x in Rn and some scalar, you can either multiply the scalar on and then plug the result into t, or you can apply the function t to x first, to the vector, and then multiply the scalar onto the result. So this, what you see here, is really t of x, which this notation here is guaranteed to be a vector in Rm, and then we're multiplying it by the scalar k afterwards. Okay, so that's what the second condition is saying. You can either multiply, if you have a vector and a scalar and a linear transformation t, you can either multiply the vector by the scalar and then apply the transformation t, or you can first apply the function t and then multiply by the scalar afterwards. So that's what condition 2 is saying, and that's got to be true for every possible choice of vector x in the domain of t, Rn, and any possible scalar that you could ever come up with. So they're very strong statements. So how do you work with these conditions? Well, here's an example where we're given a function which is called t. You notice that a lot, like I won't use the letters f and g for functions in this section. I'll use quite often the letters s, t, and u, the capital letters. T is just the first letter in the word transformation, so that's why we're going to use that letter most often, but we'll also use s and u quite often as well. So we'll define this function t. It goes from R2 to R2, so it takes as input a vector that has 2 coordinates and gives back as output a vector that also has 2 coordinates. So that tells you roughly how the function is going to behave, but here is the actual definition. And the way it's written down, it says t of x1, x2, so this is a general form of a 2-dimensional vector, and the output now is this 2-dimensional vector, which looks like it's got similar coordinates, except that both the coordinates have been doubled. Both of them have been multiplied by 2. Okay, and what we're asked to do is show that t, this function here, is a linear transformation. So we just need to verify that both of these conditions hold. So we're just going to verify them one at a time. So to verify the first statement, we need to show that t of x plus y is equal to t of x plus t of y for any possible vectors x and y in R2. In this case, we know that we should take n to be 2, because this is your n and this is your m right here, right? Look at the way they match up with the form, right? So n is equal to 2 and m is equal to 2 as well. So let's just start with any 2 vectors that are in R2. We won't make any assumptions about them except that they're vectors in R2. So that's how we're going to start. So let x, which I'll write out some coordinates for it, x1, x2, and y be y1, y2. So let those be any vectors in R2. That's how we're going to start this. And notice I've used unknown letters. I've used variables for the coordinates because I'm not making any assumptions on what their coordinates are. I'm not going to choose specific vectors x and y, because it's not enough to verify that this statement is true for a particular choice of vectors x and y. You have to show that it's true for every single possible choice of vectors x and y in R2. So that's why we're not going to make any assumptions about them except that they're in R2. Okay, well, now how are we going to verify this equation? Well, we're going to start by just looking at the left-hand side of the equation. So let's start with t of x plus y. Okay, well, what's x plus y? Well, we have coordinates for x and we have coordinates for y. Let's just write it down. X plus y. Well, they're both coordinate vectors with 2 coordinates, so the first coordinate of x plus y is going to be the sum of the first coordinates of x and y. So this is going to be x1 plus y1. And then the second coordinate of x plus y is going to be the sum of the second coordinates of x and y. So it'll be x2 plus y2. Okay, so if x plus y can be written as these coordinates, then we can rewrite this notation as t of x1 plus y1, x2 plus y2. So now you can see we have actually added these vectors up first and then applied the function t to the result, and that's what this notation is saying. So now we're going to actually apply t to this vector. So now we're going to go up to the definition of t and say, okay, what does this function do? Well, you can build the answer, the output vector over here. What's the first coordinate? It's 2x1. Well, what's x1? The first coordinate of the input vector. So the first coordinate of the output vector is exactly double the first coordinate of the input vector. So to build our first coordinate of the output vector in this case, we're just going to take the first coordinate of the input vector and double it. So we're going to get 2 times x1 plus y1. So now all of this is the first coordinate of the output vector here from the function t when you plug in this input vector. So now what about the second coordinate of the output vector? Well, go up to this definition. How do you build the second coordinate of the output vector? This is the formula right here. It's 2 times x2. What's x2? Go find it in the input vector. x2 is the second coordinate of the input vector. So I'll just to say that again carefully in language. The second coordinate of the output vector from the function t is equal to 2 times the second coordinate of the input vector. So what we put here is going to be exactly 2 times the second coordinate of the input vector, which is x2 plus y2. So we're going to go 2 times x2 plus y2. So that's the second coordinate, and now we can close our bracket. So that is our output vector. But now we need to somehow show that this is equal to t of x plus t of y. This is what we need to end up with. So, well, what could you do? Well, there's not really much that's obvious, except maybe that why don't we haven't dealt with these 2's yet, and it looks like you can see there's 2 times a sum of 2 values. So maybe we can multiply the 2 into the brackets, and then multiply this 2 into the brackets, right? And sometimes you might not always know what the best thing is to do first. So be willing to make some false starts and try some things that maybe don't work in the end. But the more you practice these problems, the more they start to become routine and automatic, and you start to develop instincts, and your gut will tell you what to do. But for now, it seems like that's probably the only thing we could do. So actually, let's multiply that 2 in. So 2 times x1 plus 2 times y1, that's the first coordinate now. Now our second coordinate, 2 times x2 plus 2 times y2. So, and this comma in the middle is the thing that separates the first coordinate from the second coordinate. So this really is a two-dimensional vector still. This is the output from the function t when you plug in x plus y. This is as far as we've gotten. Now, at this point, you might notice that we're supposed to get the sum of 2 different vectors here. We're supposed to get t of x plus t of y. So each of these are vectors. So this is going to have to somehow be a sum of 2 vectors in the end. So let's try to decompose it into the sum of 2 vectors. Now, there are a few different ways to do that, but one of the more natural ways would be to write this as the sum of 2 vectors, one of which that has all the x components, and one of them has all the y components. So for example, I can write the first vector as 2x1, 2x2, but that's, of course, those aren't equal the way I've written them. So this can't be the whole story. I have to add something else. Well, what would I have? What's missing? Well, from the first coordinate, the 2y1 is missing, so why don't I just add that here? And then what's missing from the second coordinate? The 2y2. So I could put that here, close my bracket, and then that looks like it'll work. And you can always check. What happens if I just add these vectors together now? Double check that you really do get the step preceding it. And of course you will, right? The first coordinate, 2x1 plus 2y1 gives you 2x1 plus 2y1. So that works. And then if I add the second coordinates, 2x2 plus 2y2, I get 2x2 plus 2y2. So that's simply just the definition of vector addition. We've just done it in the other direction. We've done it as a decomposition rather than actually carrying out the addition. Now, why is that good? Because each of these, they look an awful lot like other vectors that have had both of their coordinates multiplied by 2. For example, 2x1 plus 2x2. This one's a little easier to see. If you look at this, it looks exactly like the output vector that appears in this formula for the function t. So this is literally t of x1, x2, right? Based on this rule, they are the exact same thing. So this is t of x1, x2. What about this one? 2y1 2, y2. Well, my claim to you is that this is t of y1, y2. And why is that the case? Well, ask yourself, how would you work this out? If you were actually just trying to work out what t of y1, y2 is, well, you'd go back up to the definition and you'd look at what t does to its two input coordinates for the input vector. It multiplies them both by 2. So if you were to actually work this out, it would have the effect of multiplying both of these coordinates by 2, and you would get exactly this. So this second vector is exactly t of y1 plus y2. But now we're actually done proving this statement, because x1, x2, that's just the vector x. So this is t of x. And y1, y2, those are the coordinates of the vector y. So this is just t of y. Okay, so that is the end of the proof of the first statement, because we started with t of x plus y, and we showed that it's equal to t of x plus t of y, and we didn't make any assumptions about x and y except that they were in R2. So that's why we really have proven the first statement, that t of x plus y is equal to t of x plus t of y for every vector x and y in R2. In our case, n is equal to 2, right? Because of this 2 right here. So that is the first statement, which I'm going to mark off here just to indicate that that is the proof of statement 1. Okay, because when you solve problems of this form, when you're asked to show that a function t is a linear transformation, there's two parts to your work. The part where you verify the first statement and the part where you verify the second statement. Now let's finish this off by verifying the second statement. So, and you look at how we started this one. How do we start property 1? We started by assuming we had two vectors x and y in R2. Really what we were doing is start looking at this and starting with this. Right, so now we're going to look at the end to figure out what to start with. We need to show that t of kx is equal to k times t of x, for every vector x in R2 and every scalar k. So let's start by picking an arbitrary vector x in R2 and an arbitrary scalar k. So these invocations here of vectors x and y, let's call them local to the scope of part 1. Let's just say that these evaporate once this is finished. So we'll say that this is old, this is expired, and anything that we use down here is new. So we can use that symbol again. We're going to use it for the same thing, but not all the same. It's still worth thinking about why it's okay to do that. And the reason is everything that happens within this green bracket that I've drawn is just, let's take that to be local to this argument where we're trying to actually prove that the first condition is satisfied. So let's say that x, and we'll write it out in terms of its coordinates because we probably will need them, but if you don't, better to have and not need them than to need them and not have them, right? So let x be an arbitrary vector in R2, so we're not assuming anything special about it. And then we're also going to take a scalar k in the reals. So now what we need to prove is that t of kx is equal to k times t of x. So how do we do the other one? We just took our very first step. We started with the left-hand side of the equation that we were trying to verify, right? We started with this. So on our next part, we're going to start with this, t of kx. So let's write down t of kx. And what that notation means is first multiply the vector x by k, and then apply the function t to it. Well, let's write down what kx is. Right? If x is given by these coordinates, then kx, well, you're multiplying a coordinate vector by a scalar. You're going to multiply each of the coordinates by that scalar. So you're going to get kx1, kx2. So this is going to be t of kx1, kx2. Just replacing kx with what it really means. Now we can actually apply the function t. And notice that, let's compare compare this next step with our previous problem. First thing we did was actually do the operation that was inside the brackets. That brought us to here. What's the next thing we did? We applied the function t to this vector, which had the effect of doubling both the coordinates. That's really exactly what we're going to do here. First we wrote down what kx is to get to this step, and now we're going to apply the function t, which is going to have the effect of doubling both coordinates, because if you remember the definition of t, that's exactly what the function t does. It takes a vector of this form, x1 and x2, those are just labels for the coordinates here, and the output vector has, well, the same as the input vector, except both the coordinates have been doubled. So that's what we're going to have over here. So we're going to have 2 of kx1, I should say 2 times kx1, and then for the second coordinate we'll have 2 times kx2. So really, we've got 2 times k times x1, 2 times k times x2 for the second coordinate. Those brackets aren't really necessary. The only reason I put the brackets there was to make it clear that the first coordinate is exactly double what the first coordinate of the input vector was, and the second coordinate of the output vector is exactly double the input vector's second coordinate, right? I just wanted to make it clear that I really did follow this rule. Okay, so both of those input vectors, actually let's just take a step to write and without the brackets, because they're not actually helpful. Once you see that everything's been done correctly, the vectors, or pardon me, the brackets are not helpful. So I'm going to write this without the brackets, because multiplication of ordinary real numbers is associated if those brackets aren't necessary. But now you notice that both of those input vectors, pardon me, both of those coordinates of the output vector, I'm speaking incorrectly here, both of the coordinates of the output vector now have a common factor of k. So that might be worth noting at this stage, because it might not be obvious what to do now, because we've kind of done everything. We multiplied the k onto the vector x, then we applied the function t, that brought us here. What do you do next? Well, what are we trying to achieve? We're trying to end up with this, k times t of x. Right? So we want to get k times something as our answer. So hey, that argues in favor of maybe considering pulling that k out as a scalar. Right? So let's do that. Let's write this as k times 2x1, 2x2. And then, well now, the vector, if you forget about the k now for the moment, just look at this vector, 2x1, 2x2. That's exactly t of x1, x2. So this is looking good. This is going to be k, oops, I put the bracket in the wrong place. How about I just work this way, because I'm kind of running out of space anyway. I'll just work to the right now for the rest of this, because there's only 2 more steps. We'll have k times t of x1, x2. And then t of x1, x2, that's just another way to write t of x, because x1, x2 is really just the vector x. So we could just rewrite this more compactly as k times t of x, which is exactly what we wanted here. That's what we're supposed to end up with. So this was just an error, but that we started with t of kx, and we just worked through all the steps and ended up with k times t of x. And all of these steps are bulletproof. We didn't break any rules. We were very careful, so we can trust that this is going to hold for any vector x in R2 and for any scalar k in the reals. So that completes the proof of the second statement. Okay, so that is how we can say now, therefore, I'll squeeze it in down here, therefore t is a linear transformation. Okay, and that's how these proofs go when you're verifying conditions like that. On the next page, we'll actually do our best to draw a picture of what this function does, although we won't be able to draw its graph, because if we were going to draw its graph, we'd have a bit of a problem, because the input space, or the domain, is 2-dimensional, and the output space is also 2-dimensional. So you'd actually need 4 axes if you were going to draw it in the traditional way. So since we can't really draw a 4-dimensional graph, we're not going to be able to graph it in the usual sense. But what we can do is we can still try to draw pictures of what this function is actually accomplishing. But for the meantime, I'm just going to add in a comment here, which is kind of a prelude to what we're going to see on the next page. But this is an example of a stretch. And by this, I mean the function t. This function t that's defined here, this is called a stretch. Really what it does is it stretches vectors by a factor of 2. If you give it a vector x with coordinates x1, x2, it's going to give you back the same vector but with both of the coordinates doubled. And what does that do? It doubles the length of the vector. So that's why a function of this type is called a stretch. So we'll draw a picture of that on the next page.